Can you all hear me?
Yes.
Yes.
Okay. Slides are visible?
Yes, clearly.
Okay. So today we are going to see two types of processors, which is advanced, more advanced than what you've seen so far. One second. Okay. So it's VLIW and Superscalar. So this is going to be our focus today. And I would like to just touch upon this before we close the class today. And we will go into the details of this in the next session. Okay. We'll see where the break is going to be based on how fast we go. So let us see what is VLIW. If it was a face-to-face class, I would have made you guess and then got some funny answers. Not able to do it now. Anybody want to guess? Can tell me. Okay, let us not waste time on this. So it's very long instruction word processors. Okay, that means so far in RISC processor, we have seen that the instruction width is fixed and it is 32-bit or maybe 64-bit. Okay. In VLIW processors, also it is fixed. I'm not saying it is variable. If variable, it will be a CISC processor. If the instruction length is variable, it will be categorized as CISC processor. And all the RISC family of processors have a length, instruction width. But then what is the difference between a normal RISC processor and VLIW? A normal RISC processor also has a fixed length, and this also has a fixed length. Only difference is it is either 32-bit or 64-bit, which is not too big to call it as a very long. Whereas VLIW processors are also fixed length. The instruction width is fixed, but it is very long. That means we call this whole set of instructions as instruction packet. Like a network packet, we call them as instruction packet, and it has not one single instruction, it has many instructions in them. So when the processor fetches an instruction packet from the memory, it fetches all the instructions together, multiple instructions together. Okay. So that's a high level introduction. So let us see into the details. Before I go into that, I want to just bring back what we have done so far and where you are in terms of processor architecture. So we started off with parallel architectures. We said that we want to increase the efficiency of processor architecture because we want to do more work in a given time. And we wanted to increase the complexity of the processor architecture because we can't increase the speed of the processor because of the limits in terms of heat generation and cooling. So we want to put more and more hardware blocks inside the chip so that the whole chip performs better. So different ways of doing it have evolved over the time, and we are in this path that we want to increase the parallelism in while executing instructions. We want to increase the parallelism. So we thought of one way of doing it by splitting the instruction into small sub steps, and then executing them on different stages so that multiple instructions are in the pipeline on different stages. Thereby, we got some performance improvement. If ideal performance was, if it is the pipeline was 5 stages, the ideal improvement was 5 times of a normal unpipelined processor. So that we have studied enough. We also studied what are the issues involved and how to solve them. We studied about data hazards, where the instructions depend on the results from the previous instruction, and those instructions happen to be inside the pipeline. Now, we need to somehow get those results before they go to the destination register. We want to get those results in between if they are calculated, if they are ready. So we spoke about forwarding logic, and using that we try to the data hazards. And then we instructions not only do processing, they also change the flow of instruction, which are called control flow instructions. Some of them are jump, unconditional jump, some are conditional jump. So if those instructions come into the pipeline, what happens? Because the instruction flow is going to be changed. If so, how are we going to remove the instructions which are already in the pipeline and then finish those instructions which are ahead of those jump instructions, and try to avoid the damages in terms of correctness as well as in terms of time. So we thought we yesterday only saw one way of moving some instruction into the delay slot so that the pipeline is not doing unnecessary no op, but it is doing some useful job. So we saw those techniques which are not only specific to hardware, it may be software also involved, compiler is involved in terms of scheduling those instructions in the delay slot after the jump instruction, which will get executed even if jump is taken. So we saw that. Now we are not going away from the pipeline. Pipeline is going to be still there, but can we do something more so that we get some improvements? See, the evolution of these processes happened from left to right. More and more hardware logic was put into the SoCs or chips. The reason is, over the time, the technology nodes were improving. 1980s, it was 192 or 163, 64 kind of nanometer technologies. Now we are into 7 nanometer technology. So the amount of hardware logic that you can put into the chip has been increasing. That means it is shrinking. It is the minute chip layers or the chip circuitry, what you can put inside the chip, has been shrinking over the time. It has reached a case where it is around 7 nanometers now. So that means we can put in more and more logic into the chip. So we are trying to see, can I do this? Can I do superscalar? And then we will go into the multiprocessor units and multiple memory units, multiple cache. Those things are coming up in the next week. Okay. So we are into VLIW now. Now, what are they? As I mentioned, the fetch unit is going to fetch a very long instruction, which has got multiple instructions into it. Now, from the picture, you will know that all these instructions which are stored is coming from the memory. Okay. It is already stored in the locations, fixed locations. Those instructions are stored, and they come into the chip through the fetch unit in a single cycle. It may be single cycle if the width of the memory access is equal to the width of the instruction. Most likely it is going to be like that, because we have built so much of costly circuitry inside, and we cannot wait for reading this instruction in multiple cycles. It's a total waste. So if you can build multiple functional units in the chip, you can always build a larger, wider interface to the memory, which is a cache memory, not a main memory, from the chip. And cache memory is also inside the SoC. Please remember, all of them are inside the SoC. So it's a level 1 cache, which is very close to the chip. So interfacing that with a very long data bus is not a difficult thing. Why am I calling it as a data bus? Because this data bus is where the instruction is going to come in. Address bus and data bus. We call always what is read from the memory as a data, But here the data read is instructions. Now don't get confused. I am showing only the instruction memory in this picture. I'm not showing data memory there, which may be interfaced in some way. I'll show it soon. So now what happens? The longer instructions are coming. That means when I say longer instructions, don't misread it. I am not saying that one single instruction is long. One single instruction is not long. Okay. If it is so, it will fall under CISC category. If there are instructions which are varying length, and some are maybe 32 bits, some are 64 bits, some are 24 bits. If varying length of instructions are there, they will fall under CISC category, and it is a complex instruction set. It's a complex instruction set. Whereas VLIW does not fall under CISC category. It is not complex at all. They are still this VLIW processors fall under RISC category. That means reduced instruction set. That means the individual instruction widths are fixed and they are small and they are not varying. Only difference is we are packing multiple such instruction into a long word, whereas this long word is also fixed. Okay. So that means what? We can decide to build a chip with maybe 4 instructions packed together, or maybe 5 or 7 or 8. It depends on the design. Not only that, it depends on how many functional units you have in the chip. If I have only 4, I need not have to bring some 5 instructions into it. There is no use in it. Maximum I can execute 4 instructions simultaneously. So what do? We bring in based on the number of functional units in the system, and we feed them into those functional units simultaneously. In the same clock, all of them are fed and they are parallelly executing those instructions. Remember, it is totally different from what you saw in the pipeline. Pipeline also had multiple instructions into it, but those instructions were all in different stages of execution. Whereas in VLIW, mostly the execution part, okay, if I call this as the execution part, which is done in parallel. That means addition, multiplication, load or store. So load and store is also considered to be a function. So I can even combine these two from the pipeline perspective. Okay. Write back, where is it coming? It is coming here. Write back is coming here. That means all the functional units perform the operation, and those functional units could be a load store also. So I am including the load store stage of a pipeline also into a functional unit. And as you know, it needs input, correct? The execution unit in the pipeline needed inputs, operands, and it will have some output. Okay. And that output should go to the register set, which was happening during the write back stage, which is happening in a VLIW outside the functional unit. So if you map a pipeline structure and the VLIW structure, this, let me change the color. These two units, these two stages are split into multiple things. Maybe this unit may do a load, one unit may do a store, this may do an integer addition, it may do an integer division or multiplication. So now you may wonder, where are these? They are somewhere here. This decode logic is here. Okay. Then where is the fetch unit? It is very clear. It is here. So if you map, I hope this you understand what are those things are. This is instruction fetch. This is instruction decode. This is execute stage. And this is memory stage, which is accessing memory. And this is write back. So where are they mapped to? Fetch unit maps to fetch unit. There is no multiply multiple fetch units are not there. Only single fetch unit is there. Similarly, there is only single decode unit is there. But there are multiple execute unit and load and store are happening on two different functional units. So they are split into multiple units here. And write back, they all happen on the register set. So there is only one register set for the chip. It could be integer register set and another one could be floating point register set. So as I told you in the last class, there can be multiple register set, but one for integer and one for floating point. Now these functional units access them based on what they do. So once you have a linkage between an pipeline architecture and a VLIW, you will have a better idea. Now you may wonder, I didn't talk about pipeline registers. Okay, we saw, let me draw another color. We saw that there were some pipeline registers which was coming between the stages. Are they available here? If you have noticed in the picture, it's not shown. Maybe I may say that it's not shown, it is implicit there. But in reality, they are not there. Pipeline registers are not there. If at all they need to be there, it should be between the functional units, right? Because earlier it was passing the values computed by the executive unit across the pipeline register, and we were having forwarding logic to feed to the next instruction which is in the pipeline. Those pipeline registers are not found in VLIW. What is the reason? The reason is the instructions which are coming in as one set, they are all independent instructions. Independent instructions. They cannot be together if they are dependent on each other. That means one instruction is waiting for the result of this instruction. It is not allowed to be inside in the coming together. Okay, it is already blocked. It is not, you cannot expect an instruction which are dependent on each other to be given to the CPU in a single instruction packet. I will talk about who is taking care of it, but the reason why pipeline registers are not needed is that those instructions are independent of each other. They can work on, each functional units can work on those instructions, assuming that they have all the operands required for them and they don't need to wait on some other instruction being executed in some other functional units during the same time. So this would have given you a good overview, but I hope so. Let us go further and spend some time. Okay, this you keep it in mind. If I compare a VLIW processor with a pipeline processor, how do they match? How do they map into each other? I will repeat again once for a summary. There were 5 stages in the pipeline. First was instruction fetch. There is one instruction fetch unit here also. And in pipeline, there was an instruction decode unit at different stage. And here also there is one decode stage, which decodes the instructions and feeding it to the functional unit. And in the pipeline register, there was one executable stage, whereas we have multiple execute stage. And we had a specific stage in the pipeline, which is a load and store operation to interface with the data memory, which is not shown here. Here, the functional units do the job of data store and load and store, because they are all connected to the register file. You can assume that this particular thing does not have a load store shown. Okay, don't think that it will not be there. It has to be there if it has to be a full-fledged processor. So you can assume that it is connected to some data memory, one unit, which is also may not be taking operands, because load store did not have to take 2 operands. It may take 1 operand. So this picture is not completely full-fledged VLIW. I will come to that and show you. So load and store stage of pipeline is also separated into a single functional unit, and there are no pipeline registers found in VLIW because the instructions which are packed together, they are all independent and they don't depend on the results of other instructions. So we don't need a intermediate values to be passed to the instructions which are all executing together. Now, one more question to answer. Can I load another long instruction, assuming that one unit has finished the job? Maybe integer unit has finished it, whereas floating point unit is still doing. Can I use that by reading another long instruction and then passing only an integer operation to go through? The answer is no. So we need to wait for the complete instruction to be executed before taking the next one and feeding it. I'm not saying that you cannot take it from here. You can take it and buffer it here, but decode and then allotting the job to the functional units cannot be done until all the functional units complete their job. Remember, they do not complete together. That's another difference. In pipeline, we try to find out some means of the executive unit also finishing irrespective of what it is doing, so that pipeline is full always, there is no stall, everything takes single cycle. That's what our logic was. Whereas here, I cannot assume that because these units are of different purposes. One is for integer operation, one is for load, and one is for store, one is for floating point operation, and one is for divide and multiply. So they need not have to be completing it simultaneously in the same cycle. So when I am packing the instructions together, I have to keep it in mind that some units may be idling while some other units are busy doing something. Okay. So I have given enough input now, and I can actually run through the slides now a little faster. VLIW processors, as the name suggests, is a very long instruction length, maybe 64 or 1024 bits. Okay, even 64 is small enough. It will be 256 or 512 or 1024 bits. Okay, not 1024 bytes. I'm not saying 1 kilobytes. Please don't misread it. It is bits, one instruction bit. In each fetch cycle, one instruction packet, I'm calling this whole thing as a packet, is fetched from the memory and then fed to the execution units. They are all called execution units in the CPU. EUs execute instruction fed to them in parallel. They all run in parallel. Okay, they don't have to depend on each other because they are not waiting for the results from other ones, so it can run for parallel, and they all access the registers set. And one more thing is, they take, similar to our ALU, they take two operands and write back one result. Okay, so that's why I'm saying they're all not a load store unit. It is some functional units which is performing some integer operation or maybe floating point operation. And if it is a floating point, maybe register file will be split into two. We'll see. Okay, don't assume too many things about this particular picture. Now, functional parallelism is achieved by having multiple EUs executing instructions in parallel, operating on a common register file. They all operate on a common register file. That means they take the operands and write the results back. So if you recall, in the pipeline, ALU was accessing the register set, right? It was accessing the operands in the ID stage, and then it was fed to the ALU through the pipeline register. And I told you that time the register set is a multi-port register set. That means two reads can happen simultaneously and one write can happen, because that is what is required during the pipeline stage in that kind of a design. But if you look at this, the same number of ports will not be sufficient. See, what I call by port means, it's, see, register set is a collection of registers in the processor, like R0 to R32. And port is a way of reading one of the values into it, out of it, okay? Or writing something into the register set. It's like a entry point and exit points. So the question is, when I say a register set is multi-port, whether multiple reads and writes, can it happen simultaneously? There should be some hardware logic built into it so that there is no clash if there is a write happening to the same register. See, if I say that there are 4 write ports, okay, if there are 4 write ports available to the register set, then I am allowing 4 functional units to simultaneously write into the register set. In that case, there is a possibility that all of them are trying to write into the same register. Can it do it in the same cycle? It's not possible, because the signal variations during the same clock cycle, if too many people are writing into that, if you know that a flip-flop takes the input and then latches it, if too many people are driving the input to the flip-flop, you will not have a stable 1 or 0 state at the input of flip-flop. So it will not be able to read a single proper value. It will be some mix of some random junk going into the register. So it cannot allow. Maybe you can delay and then allow one after the other. So there should be some protection to take care of multiple writes happening into the register, to a particular register. Can it happen on different registers? Yes, of course. Suppose if this register file has some 64 registers and all the functional units are accessing 4 different registers and writing into that different values, 4 different values into 4 different registers, it can happen simultaneously during the same cycle. So there should be some circuitry to take care of those, decoding it, what is the register it is trying to access, and then allowing it to write it. And if there is a clash, if 2 functional units are trying to access the same register, there should be a logic to prevent it and then sequentialize it so that one after the other may be written, or some mechanism has to be provided. So when I say multiple ports, it means multiple operations happening on the same set of registers. Now, can read happen parallelly? No issues. Can the read happen from the same register simultaneously? No issues. As long as the bus and the driving circuit, I'm going a little bit into the details of electronics because you guys know it. If you remember, fan in, fan out, I told you some time back. Fan out means how many circuitries can be connected to one output. How many you can connect? That means the signal which is driving 4 different circuits should have enough current supplying capacity to feed those 4 units so that all of them read the right value. If they are not able to get the correct value, then what happens if it is a driving circuit is low power, it's not able to drive multiple things, then the voltage level will go down and the 1 will be read as 0 and vice versa. Anything can happen. So you have to take care that if functional units are so many and all of them are reading from the same register, then fan out should be at least 4 so that all 4 can be read. But it is not 4, it should be 8, because nobody prevents a functional unit read to both the operands from the same register. It can read R1, R1, EU also can, this also can read R1, 2 R1s, this also can read R1, and all of them can read same register. In that case, fan out should be 8. So you have to apply what you have learned earlier into this. Okay, cross pollination of knowledge learned in different courses you have to do. Because I taught you many courses, I am able to relate and then tell you that I know what I told you and what you know. But even if it is not there, I have not taught you DSP, I have not taught you FPGA. Now what you learned there, you should be able to connect with this and then see, is there any linkage that you get? Is there anything that you can think whether this processor, is it similar to a DSP processor? Did maybe Sandeep would have mentioned you about the DSP and VLIW in his course. So think about those things whenever you learn something. Try to correlate what you learned in other courses. It will always make you good engineers. Okay, so they all execute in parallel, I told you. Now let me show you another one, which is a complete full VLIW architecture. Whatever I told you is all there. It has got multiple integer functional units. It has got a load store unit. So what I mean by load store, that means this block is capable of doing both load operation as well as store operation, but not simultaneously. Remember, it can take a load instruction and perform the load operation. In the next cycle, it can take a store instruction and perform a store operation. No issues. Similarly, this also can do. So if I ask you a question, in the instruction packet, can I have two load instructions packed together? You should say yes. Can I have two stores together? Yes. So if I have a load instruction and a load instruction here, no issues. Both of them will perform a load operation. If I have a store and store, both of them will do a store operation. No issues. Now, another question. Can I have a load operation, load instruction in this place? A big no. You cannot expect a function for a floating point unit to do a load operation. It doesn't even have a connectivity with the data memory. How can it perform? So it is illegal. It is illegal to have a load or store operation fed to any of other fellows. Similarly, I cannot have an integer operation coming to this stage. It is illegal. So who takes care of it? We'll come to that. It is assumed that the slots are filled with the instructions which match with the unit it is connected to. Don't think that this can be changed. This connectivity is a hardwired connectivity. You cannot change it. So what can you do? You have to make sure that proper instructions are given to the CPU. If you do it wrong, runtime exception will happen. Illegal instruction, or it may keep quiet and do not perform the job, but which is not as actually a CPU should do. Even before it comes here, the decode logic will catch it. It will know that I am expecting either load or store in this. I am getting something else. Hardware logic can verify it, and it can raise an exception to say that this instruction packet is illegal, is corrupt. See, it's not that an illegal instruction is coming intentionally. It could come because of some memory error or a file corruption. You have built an executable in your hard disk, and one of the bit has got corrupted, and the disk unit did not find out, and the instruction came into the instruction memory and then coming here. What will happen? One bit change can make the load store instruction look like a floating point instruction. We don't know. It depends on how they have encoded the operations in the opcode. They might have put some distance between two opcodes so that this kind of one bit error doesn't land into this kind of trouble, but we never know. So information encoding, what you have studied, you can bring those logic here. Okay. So one thing you understand, these instructions slots are reserved for a particular kind of a unit. So you can only put those instructions which can be handled by this unit. Suppose this internal function unit can take care of add integer, subtract integer, multiplication of integer, and division of integer. Then you can put any of those instructions here. You can put all multiply integer instructions here, and all of them will perform a multiplication job. There is no problem. But you cannot put a floating point operation here, and then, or you cannot put an integer operation here. It is not possible to. It is not allowed. Okay. Now look at this. This is a very interesting thing to understand. Before that, let me talk about one more thing. I don't know how many of you notice this. There are 3 inputs given to this floating point unit, whereas there are only 2 inputs. If any of you are getting the reason, you can tell me. Okay. I will talk about this now. I want you to think why there are 3 inputs. I am sure many of you have taken DSP as a course. So the answer lies in what you learned in DSP course. Okay. That's all I can give a clue. Someone can message me, chat, okay, on chat. Okay. If you have sent and I'm not seeing it, please tell me. I think the chat window is open for me, so I will know. Okay, guys. While you are thinking about this, please listen to me. You have multi-core in your brain. I'm sure you can think. Data memory. I said both can do a load operation, both can do a store operation. How is it possible? So far you have studied that memory is having only one interface, only one address bus, on one data bus, and it can perform only one operation, either read or write, one signal saying read / write bar. These are all what you have studied, which are some 20 years back what was happening. What is there currently is a data memory which also has a pipeline inside. Okay, a data memory has a pipeline, and it can take multiple read or write commands coming from the functional units. In this case, it is not a CPU really, because CPU is the whole thing. This is one functional units in the CPU which is interfacing with the data memory. So far we studied that only CPU puts the address and data. You have to unlearn many of the things. Okay, what you see will be different from what you studied. It is because we cannot teach you what is currently being used. We can teach you from the beginning how it is evolved, but the problem is the gap is very wide, so you have to adapt. Now what you see is totally different. You have to keep reading. What you know about memory is very little. So this memory has a pipeline. It can take multiple commands, read command or write command. That means what? Those read and write commands can be for different addresses, and then it can issue the data memory inside for it to give the values, and then after a few cycles maybe it will give the data out, and it remembers which command came from which bus, and then matching bus it will send out the data. So what I mean by that, this data memory is capable of handling multiple read write commands simultaneously, in this case at least two, and it can store the pipeline. There is a pipeline of commands it can receive, and then it can feed the data. So that way it can perform much faster and efficient. Okay, now one more thing, try to understand. Address is coming from here. Why? If you recall, in our pipeline stage, the load and store instructions were computing the address based on indexing or indirect addressing, or shift with the shift and then indirect addressing. Lot of things we learned about addressing modes. So all of them are supported here, or maybe many of them or some of them. So address has to be generated by this guy. Now where is the data coming? If it is a write, if it is a store, if it is a store operation, it is storing some register value. The register value could be coming from here, or it could be coming from here, based on what is being stored. If it is storing a R1, then it is coming from here. If it is F1, it is coming from this register. That's why you see that there is a connectivity happening to both. And similarly, if it is a load, it is address is coming from here, but loading may happen into one of the registers from a memory directly into the one of the register files. So it is connected like this. I want you to think about each of those signal directions and understand what is getting passed between them. That is how you read a hardware circuit. Okay, many of them may not document everything, that you have to understand it yourself. Okay, I didn't get any answer for why there are 3 inputs for a floating point, and I gave a clue that it is in DSP operation, one of the DSP operations. Have you heard of MAC operation? Multiply and accumulate. How many operands are needed for MAC? Okay, this is the MAC operation. Oh, sorry, it is a multiplication. Okay, it is a multiplication. Multiply B and C and accumulate it over A. If you have seen floating in a DSP algorithm, either FFT or DFT or whatever you have seen, coefficients will be there and some other value will be there, signal. It will be multiplying it and adding it. Most of the time, it will do a multiplication of 2 values and keep accumulating the values, because a series of multiplications are getting added. So if you are to perform such operations, you will naturally do it in floating point. You won't do it in integer, because these are all signal inputs, image processing, or it could be a voice processing or anything. So they need to be floating point numbers, and this is a multiplication. You have to multiply and add. So those things are coming from the registers, and this unit does the MAC operation and puts back one result, which is accumulated value coming out. Okay. So they're all getting written into the registers. That's why you see that there are 3 inputs to be shown on a floating point. And I mentioned about a memory, which is a synchronous DRAM, okay, which does this job of multiple address, reading multiple data simultaneously, commands it can take, and then give out the values out through this bus. Okay. I hope this is clear. This picture is a very good picture showing you clearly what is happening in VLIW. So I will repeat and summarize now. Instructions are fetched. That fetch logic is not shown. Okay. One instruction packet at a time, and the locations of those instructions are fixed based on where they are mapped to, which functional unit they are mapped to. Those things are fixed, and whole whole instruction packet is executed by multiple units, and they parallelly they do access the registers and finish off the values, finish off the work. Once all of them complete, the next instruction is fetched. Next instruction packet is fetched, and multiple instructions get executed. Okay, I have a quiz now. If at all you are sleeping, please wake up. I think I have given this earlier answer. So tell me, if I have to categorize this processor as one of them, which one would I do? Is it SIMD, SISD, MISD, or MIMD? So let us see. What do you give me? Shall we stop the poll? 38 out of 48. Okay, 42. Okay, I will stop it. I will share it. So there is a majority saying it is B, and C and D are equally split. Let us first see which is completely ruled out. Okay. SISD, single instruction, single data. These 3 people I have to talk to, it is not SISD. It's not single instruction. Okay, you may think that it's single instruction packet, but there are multiple instructions inside and there is a parallelism happening. Okay, multiple execution units are there. So it's not SISD for sure. But you might think any of them could be falling under this category. It depends on how do you view it, and it completely depends on that. And I don't think any of you made anything wrong in choosing any of those three. Okay, I would say A is wrong to be clearly it is wrong, but I won't say that if you have chosen SIMD or MASD, I might give you a bit of freedom, but maybe I may be very, why did you say this? I may say it is not a single instruction. Okay, when you say that there are multiple data, okay, your multiple data is true. There is both integer register is also accessed and the data floating point is also accessed. MD, I agree. Why SI? Okay, it is not that same instruction add is working on multiple data. So even I would say SIMD is little on the wronger side, and maybe this you may have a confusion. So let me tell you how to resolve it. Okay, I am saying that it is this and it's not this, but you can even think this is like this because multiple instructions are coming. Yes, it is true. Is it not accessing multiple data? Yeah, of course it is accessing. So you may say that it is MAMD. Let me explain why I am saying it is not, and when I say it is MASD. See, here the data is not specific to a particular register. We are not saying that if it is read from R1 and R2, it is multiple data. It is little bit higher than this. Now, abstraction level is at the application level. It is at the application level. And whether the data, what it is being read, there are belonging to a single application or multiple applications. Okay. Or are they totally unrelated data? Instructions are not dependent on each other, I mentioned, but that doesn't mean the data is not dependent. In the sense, they all belong to a one common application. If you are performing a matrix multiplication, this matrix data is a image pixels of a particular image. While you are processing multiple data here, they all belong to a single data. So I can call it as a single data because it's for the same image. Okay, so it's little controversial or it can be debatable. It is, but the literature normally categorize the VLIW as MASD than MAMD because there are some architecture which are specific to the MAMD. Okay, which are the data is coming from totally from different applications and working on multiple cores are applying, working on it. Multi-core processors fall under that category, whereas a single core working on an application fall under this category. So for that purpose, I would say it is this. Okay, no problem. Even if you have made it any of those things chose wrongly, it's okay. Fine. Quickly, let me cover this. I told you that instructions are grouped, which are not dependent on each other. Now they are coming one after the other. Let us take this instruction. B, C, I can have same register appearing as an input. B is appearing in both. These are all inputs to this instruction. I can read multiple inputs. Still, I will call these two instructions are independent and they don't depend on each other because this is writing the result into D, whereas this is writing result into A. They are two different registers. So they don't depend on each other. In the sense, even if it is writing into the same register, it's not dependent. I won't call it as a dependent. I will call it as dependent only when one result is required for the other. Suppose this is writing into A and you want one of the operands to be read from A. Then these instructions will become dependent instruction because this has to be done and then it has to get it. which is not allowed in VLIW. So any of the destination registers will not be one of the operand registers. That's all. Very simple logic. And mostly even the destination registers will be different, because I will tell you the reason. Even the destination register need to be different because there is no ordering of this instruction is captured. Let me explain one more thing, how these instructions are fetched. Okay, now I have not spoken to you till now about how these instructions are fetched, from where they are grouped, who is grouping it. I have never spoken about it. So let me now come to that stage, because if you are to understand this, you need to have that idea. Like a typical program, instructions are always sequential. Remember, they are sequential. There are individual assembly instructions generated by the compiler, which are to be executed sequentially. Now, a normal compiler will generate the instructions like this, based on the high-level language that you have program you have written. And then the VLIW process compiler, meant for VLIW, does one more job. It does one more job. Apart from generating the instruction, it is given another job to group those instructions such that the independent instructions are grouped together. Okay. Independent instructions are grouped together to form a instruction packet. And we have to make sure, while the compiler is grouping the instructions, the ordering is, the data dependency in the sequence is not disturbed. Only thing what it is supposed to do is pick those instructions which can be executed independently, and those instructions are not dependent on each other for the values, then put them all together in a one block. Okay. It is not only that you choose instructions based on which are independent. The compiler has to think about the hardware units which are there in the system, and where it is located. Okay, when the instructions are coming, they are coming in this particular order. So if I am grouping the instructions, I have to group the integer instructions in this location, another integer instruction here, and maybe one floating point instruction. If I don't find a compiler, I am talking about compiler does not find an instruction which can be grouped together, then leave it empty. It is not that you have to put something. If there are no instructions which can be parallelized, which can be grouped together to be executed simultaneously, it is unutilized. That block is not utilized during that particular cycle. So choosing the instructions and grouping them is done by the compiler based on three conditions. One is no dependency is there, they can all run in parallel. Second, you have to choose a location where you want to put those instructions. There is a unit which can perform the job. And third, if you don't find such instruction, leave it blank. Okay, so you have to make sure that proper instructions are chosen which are independent of each other and do not have any dependency. The sequence is maintained, and we have a proper location available for that instruction to be put. So it will go through the instructions in the same sequence. Do not think, remember one thing, if suppose it is not able to find one instruction here, it cannot go down the line and then pick something which is some integer operation. It has to remember that data dependency, whether this instruction depends on something has to be performed before. If you remember in the embedded system course, I talked about data flow analysis, compiler does. It has to do it, and it has to schedule the instructions in and then group them all into single instruction packet. So Once it is done, they are all put in together as a very long instruction. So that is what you are seeing here, and it has taken care of all those conditions prior to the generation of executable. So compiler does it. Who does the instruction scheduling? It is the compiler. Is it dynamic? No. It is fixed, statically scheduled instructions. Why I am calling it as fixed or static? Because it is not changed during the execution time. Anything that changes during the execution is called dynamic. Anything is not possible to be changed is called fixed or a static. If you remember, dynamic linked library and static library we spoke about in the system programming course. Static library means the library is built into the executable. During the execution, the library is not dynamically loaded or unloaded. Whereas dynamic link library means library is used or loaded into the memory only when it is needed during the execution. So it is dynamic. So the static and dynamic words are used consistently in the computing world. Here, static scheduling of instruction means during the execution of instruction, you cannot change the location of the instruction, or you cannot choose. I cannot say that, oh, okay, let me move this instruction here and let me move it here. No, processor cannot do. It is done statically at the compilation time, and processor has to just execute it. That's all. It is called static scheduling of instructions. Okay, and who is doing? Compiler is doing. Now, by now, I am not going to explain every parameters. You should be able to understand it. So each of those things are getting executed, and this unit is not used during this time, and next cycle this is done and this is done in the next cycle. So you might wonder why this is not scheduled ahead here, because it is waiting for this result, this result here. Similarly, it is waiting for this result to be available for this instruction to be executed. So even though I have a free slot to perform the floating point multiplication, because this unit is not used during this slot, I cannot schedule this instruction here along with them, because they are only computing the value which is needed for this instruction. So it's not possible. That's why it is delayed. Okay, I think that much of explanation is required enough. You should be able to understand. So this is called fine-grained data parallelism. At the instruction level, based on the data dependency, we are grouping the instruction. It's called fine-grained, and SDRAM is used. I have already told you why SDRAM is used, and it is meant for DSP operations. Intel, Titanium, and AMD's GPUs fall under this category. Okay, so GPUs are good examples of this type of processors. Okay, now let us talk about instruction, how it is grouped. So I have shown you that these are all different instruction: load, store, everything is inside. And if you expand one instruction, you will see that it's an add and register 1 and register 2. Maybe one more will be there if it is a 3 operand. Okay, here what happens, the destination operand and one of the source operands are same. Okay, there are some Intel assembly instructions wherein the destination register is same as the one of the operand register. So if this is add, it is a register 1 plus register 2 written into register 1, or maybe register 2. Mostly is register 1. So 2 operand instructions also possible. Okay, so VLIW architecture, whereas pipeline is breaking an instruction into multiple unit. I explained already. So this I have already explained. They are done by multiple functional units. These are all for your future reading. I'm not going to read up everything again. One more thing is, normally VLIW processors have a bigger register files, and VLIW compilers do the static scheduling of instructions, which I explained just now. Compilers finds out which operations can be executed in parallel in the program. Compiler groups together those operations into a single very long instruction word or a packet. It's called instruction word or instruction packet. Compiler ensures that an operation is not issued to be run on the CPU. When I say issued means it is put into a particular long instruction word. It is not going to schedule particular instruction in a slot unless all of its operands are ready. Remember, if it is putting some instruction into this slot, operands required for this instructions are already available by executing the at least the previous instruction, if not the earlier. Okay, at least the previous instruction should have computed the operands needed for the next instruction. That's all. It doesn't have to bother about whether it is always assumed that the previous instruction are all completed when the next instruction starts. So it is implicit, it is accepted, it is allowed. Okay. Okay, one more I'll show you. It's just to show you different pictures. That's all. No, there is no other intent. Instruction cache is there, and long instruction word is coming in, and then multi-port register file, and this is what is connected to data cache. But don't think that this cannot be written into this. This can be written, and there is a bus interface. So I picked up some different pictures to just show you how to understand when you come across different architecture pictures, how to read it and understand them. Okay, that is very important. And I'm not going to go into the detail. I have repeated the whole thing. In fact, this is just a repetition of what I have shown you. Okay, now before I end it, let me do one quiz. Okay, before we end the break, I want you to tell me, if I store, these are all the instructions, okay? Different instructions are shown. I want you to tell me whether all functional units are used in this or not, okay? Just one quick poll before we break. Okay. Anybody has any doubts or anything, you can ask me. Okay. Looks like all of you want to take a break. Answer fast. Don't think too much. Assume that inside the instructions are all, there are some instructions, okay? It's not talking about a particular unit because I'm showing you what is inside the instruction. So nothing is blank. So actually you can choose yes. Okay, very good. Majority of you shown the answer, given the answer. So all these different instructions are all performing the job. See, compare, not zero, add, FP multiply. If you see that they all belong to those blocks, okay? Compare is done by the integer ALU. So add is done by this. Mul is done by integer multiplication. Load and store are done by this unit, memory unit, and branch is done by branch. So maybe one thing is more in this case. This we never saw branch unit being there. So it is very important. Actually, I would say that this is the complete VLIW processor because it has the branch also shown. So any branch instruction will fall under this particular block. These units cannot perform branch operation. Only this will be able to do a branch operation because loading into PC, those kind of things are all done by this unit. Okay. So I think you guys got it. Answer is yes. Let me see whether anything else is there. Okay, only one. Sorry, I forgot about this. I will leave it as a homework. How is these operations are done in a normal sequential processor, how the sequences are done, and how is it done in the VLIW. I don't want to explain. I am sure you will be able to do it. I will change it to homework so that you guys really do a homework. This is simple, a comparison of different processors. I will tell you one thing to remember and understand. There is no microcode. What I mean by microcode is when you want to execute one instruction, suppose a compare or a load or store, it is done by multiple control signals given to the units. If you remember the original unpipelined CPU, when I showed you some simulation in the computer organization course, as well as in my session 1, I showed you it is generating sequences of signals to take inputs from different registers and then putting it in the MA or memory address register and getting the value from the memory and then putting it into the register. So there are so many things, operations happening. So those signals are stored as a microcode into the program, into the chip, and then based on the instruction, those microcodes are executed. So CISC was having those microcode, okay, whereas it was not there in the CISC. Okay, CISC, sorry, I'll repeat again. Microcode was used in CISC but not in RISC. The reason being, RISC are simple instructions and they all normally happen in single cycle. If it is happening in a single cycle, you cannot have so many control signals generated within a cycle. It has to be done across the cycles. Okay, one set of control signal per cycle. So no microcode here, and VLIW is also a RISC processor. Okay, only here microcode is allowed because one complex instruction takes multiple cycles to complete. So as a processor architecture students, you should know what is a microcode and where it is used and where it is not. If you need to execute an instruction over multiple cycles, you need to generate different control signals to control the data flow within the CPU, between the registers and ALUs. Then microcode is used. Microcode is like a set of control signals generated. In RISC and VLIW or any other processes, we have within a cycle one instruction is get completed. So we have a hardware logics which are split into multiple small units and they run at a very high rate. So you cannot have a microcode program running there. But I will show you something in the next lecture where the microcode is used. Hold on, okay? I'm explaining more on microcode because you need this knowledge to understand my next topic. So we stop here for a long awaited break. What is the time? Okay, 2:15. So let us meet at 2:25. My wife is saying 2:30, but I am saying 2:25. 2:30. I think we'll do it at 2:25. 2:30.
Yes, 2:30.
2:30, sir.
Hey, 1 second. Let me. Okay, shall we start? Okay. So today I will complete Superscalar processors, and then I wanted to touch upon the next topic, which we will defer it for tomorrow. Okay. So let us start. Now, where are we? We are done with VLIW now. We are getting into Superscalar processors. It's a next advanced stage, advanced processor architecture. Okay. I'm going to give an introduction today, and tomorrow we will talk about some implementation of this Superscalar architecture. That's a topic. So let us see what these words mean. Base pipeline, super pipeline, and superscalar. Base pipeline is simple pipeline architecture, which we have seen in the few classes ahead of it. Only difference what we have seen as 5-stage pipeline. Here I am showing you 4-stage pipeline. It doesn't matter, okay? That can be 3-stage also. ARM7 has 3 stages. So there are different processors with the different stages. Only thing here is overlap is happening on every cycle, and there is a new instruction coming into the pipeline every cycle, which we have seen, and it is completely overlapped. All the stages are overlapped. And the gray or whatever this design is for execute stage. Okay, we are going to differentiate the execute stage separately because we try to parallelize this stage mostly in different architectures. If you see the common idea, VLIW, what did it do? It actually tried to parallelize the execute stage. It didn't do anything with the decode. It didn't do anything with, instruction fetch or a decode, and write back can be only one. Maybe multiple units are writing into it, but there is one register set where it is written into. But what is parallelized is this execute stage. So mostly in the architecture, what we are going to see tomorrow, as well as what we are going to see today, and in VLIW, we saw that parallelism is done during the execution. Why is it so? That is the most complex stage in a pipeline. If you see, fetching is simple, sequential fetching, or it could be because of branch, it may go into some other location, but it's a simple routine job of fetching instruction from the memory. There is nothing to innovate, nothing to parallelize much. Decode is another simplest logic where once the instructions are fixed and the format is fixed, it is a simple thing. You and me can design one decode logic. Once opcode is fixed, try to take the input, and then based on that enable one adder or a register operand. It is a very simple logic which we can design, anybody, and it can be implemented without much of difficulty. Whereas execute stage differs from instruction to instruction. If you see decode and fetch or write back, they're all more or less same across instructions. Whereas the uniqueness comes in the instruction based on what it is trying to do in terms of execution, whether it is addition, subtraction, integer, floating point, branch, or memory access, load or store. Everything is in the execute stage. So that is the most complex part of the instruction pipeline. And every instruction architecture is trying to do something innovative in terms of improving the performance specific to execute stage. That's why you see that it is separated out. So in a base pipeline, every clock cycle, one instruction comes in, and there is one instruction on each stage during every cycle. Assuming the pipeline is full and it is 100% occupied and there are no holes or bubbles in the pipeline. ILP processors that we have seen so far and fall under this category. Now, what is this super pipelined? Super pipelined goes from one level complexity, increases the complexity by one more level. If you see, this is the timeline. Every clock cycle, what is happening? In a pipeline, different instruction, if I see this fully occupied pipeline, this instruction is here. At the same time, this instruction is execute stage, and another instruction which came next is in decode stage, and this one is in fetch stage. So different instructions occupy different stages in a cycle, but not more than one instruction. It is always maximum one instruction can be there in a particular stage during a cycle. Whereas if I draw the same thing here, you see that there are two instructions during this time. And here there are two instructions. So at the same time, there are two instructions occupying a particular stage. Okay. More than one instruction will be there in a stage, because each of this time gap is for a stage. So if that is true, if you see here during this time, there are this is fully there and this is halfway through it's entered and then half is starting. So at a given time, you can see that multiple instructions are in the, say, multiple instructions present in a particular stage. So a super pipelined processor can have more than one instruction per pipeline stage per clock cycle. So more than one instruction per pipeline stage per clock cycle. So here there is only one instruction completely occupying a stage. But during the same time, multiple instructions are there, but they all are different stages. They are all not on the same stage. The hardware execute stage, if you take example, it is going to process only one instruction at a time. It's not going to process two instructions at a time. Whereas in super pipeline, it is one execute stage may have multiple instructions getting executed. Okay. So it is a little more complex. So it's called super pipeline. And the next stage is superscalar. Superscalar is you just have a duplicate pipelines, multiple pipelines you have. Okay. Intel processors have some U and V pipelines, multiple pipelines. There are separate pipelines taking instructions, various instructions parallelly through the pipeline. So if you have a multiple hardware pipeline in a processor, it's called super pipeline. So there will be a set of instructions through this. There will be another set of instructions through this. And similarly here, that means what? More instructions are there in different stages of execution in a super pipeline or superscalar processors. Okay. So now we will see some examples. Right now, you may not have a clear idea. Let me explain now. This picture I showed you something similar to this for the online simulation tool. I said there is one instruction fetch, one decode, and now decode and operand fetch are divided. Some of the Intel processor or most of the Intel processors have different stages for these two. Not like a RISC or a MIPS processor where these two are done in a single stage. Operand fetch is also done in ID stage. Whereas Intel processors or even other processors, many of them in the market, they do this, they divide it. They do a sub step of this operation. They do it on two different stages. That means what? One instruction can be in a decode stage, another instruction can be in operand fetch. So they are done in two different stages. Whereas in MIPS, it was done together. Okay. Whereas you don't see a memory stage here separately shown. In this case, even that unit is not all shown. Maybe in a typical VLIW, we saw that we had a load store also as an executable unit. Okay. So there is possibility that you will have it, because you cannot have a processor which does not have a load and store. Why? It doesn't make sense at all. You have to have the data in the memory and there should be some instructions to access them. Otherwise, what can you do? How will you bring the values into the registers and perform this job? So you cannot have a processor without a memory interface to the data for storing data, retrieving data, because registers are not enough to perform. If it is purely register based, it must be like an FPGA with so much of hardware built into it that it can perform all the operations within the register, which is very, and then do access to the memory. So there will be some unit to access the memory. Okay. So multiple instructions, in this case, multiple instructions can be in execute stage per clock cycle. Wherever you see a multiple instructions are there in a particular stage, then you can easily differentiate that it is something super. You have to add a word super when you have an instruction, multiple instructions are there in a single stage. So execute stage, there are multiple instructions. So it falls under super pipeline category. But normally the literature, architectural literature, they don't differentiate between super pipeline and superscalar. They merge them. So don't latch on to one particular word and then think that it is the way it is defined. Okay. So if there are multiple instructions in a single stage, it is called super pipelined or super scalar. You can call any of them. Both of them are valid. So super pipeline processes, in our discussion, we are saying that there are no multiple pipelines. It's a single pipeline with multiple execution units is super pipeline. Okay. If you want to separate out what is super pipeline and what is super scalar. Super scalar is something which has got multiple pipelines, replication of duplicate pipelines, complete pipeline. In super pipeline, it is little lower than that. It has a common stages and then only execute stages multiple units. So if it is not completely replicated, it is super pipeline. And if the whole thing is replicated, it is super pipeline. Okay. Sorry, super scalar. So the block diagram above shows a processor where two integer ALUs and floating point ALUs are there. And based on the instruction which is fetched, operand will be fed. And then after getting the operand, along with the operand, you give it to the unit. Remember, a unit will start executing the instruction only when all its operands are already ready and available. It will not come into the integer unit and then look for operand. Okay. It is like this. When you go into an exam hall for writing the exam, you are already ready with answers. Most probably, you should execute an examination with all answers ready. Okay. And then you write back into the paper. You think in the exam hall and then give the results and then write back, give the paper back to the teacher. So that's what is the execution you do. So functional parallelism is achieved by having multiple functional units capable of executing the different instruction in parallel. Okay. So in many literature, I told you super pipeline and super scalars are synonyms. So they may actually refer a super pipeline processor as super scalar. Okay. So don't get confused. Even if they are calling it as like this, it is allowed. There are flexibilities are there. Okay. Let me show you some diagram. Now, I will explain you when you see such diagram, how will you understand it? Where will you start analyzing the picture? Always start from outside world and then come inside. There is a bus interface. Okay. That is an input to the unit. So come from always when you enter the house, you will enter from the entrance, not from the window, right? So let us enter through the entrance. Cache memory comes, memory management unit comes. Why memory management unit comes? It's a conversion of virtual memory to physical memory. And then why cache memory comes? Because this is the highest level of hierarchy in the memory system. And why is the bus interface unit? It is to connect to the main memory or maybe the second level caches. So you come from there. Okay. What is coming in? Initially, it has to be instruction. So instructions are coming. Now, since we have, then come inside and see that there is an integer processing unit, there is a load store unit, there is a floating point unit. Now, integer unit will talk to the integer general purpose registers. Floating point unit talks to floating point register. Talks to means it reads writes into it. Both of those register set are connected to the load store. Why? The values from here has to be loaded here. Values from here has to be stored or loaded. Both operation needs to be done. So interface is there. That's why you see that it is direction is both. Now you may wonder why is this single way? It should have been this way. All the pictures are not ideal, perfect. You have to know where to correct it. It shows only this. Okay, I can understand it that it is writing into it. So they are not showing it here. Only address is coming and the data is coming through the unit. Okay. So there is something done here. Let me explain you what it is here. I have not explained you what is this and what is this. Let me talk about it first and then explain you what is. Now we are talking about a superscalar CPU wherein we have multiple execution unit. Now I have to differentiate between this and the VLIW. VLIW had multiple instructions coming in, okay, and they are all packed together. They were all packed together as a single instruction packet. Whereas in Superscalar, these instructions which are likely to be executed in parallel are not packed together as a single long instruction. They are not packed. They are coming into the CPU one after the other individually. Those instructions come in individually. No compiler or any tool is looking at the instructions for parallelism and packing them into one small long word of instruction. They all come as individual instructions. Now, who is deciding which instruction will go where and when? It is the hardware. Which hardware? This hardware, which is instruction issue. So, a major difference between a VLIW and Superscalar or a Superpipeline. So, I am not going to talk about Superpipeline. It's always Superscalar. Is the instructions come individually as what the user has written or compiler has generated. There is no packing of instruction done by the compiler, which is called static scheduling. The scheduling of instruction, running them together, was taken care of by the compiler during the compilation stage, and it is fixed when it is generating the executable. That's why it's called static scheduling. Whereas in a superscalar processor, there is no job done by the compiler to parallelize the instructions. It doesn't look for whether load is there or store is there or integer float or any operation. It doesn't look at all. Whatever the higher level language you have given, it will generate a set of instructions and then give it to the CPU. CPU reads them, reads instruction after the other, one another. And in the hardware, the dependency or dependence analysis of instructions are done. Which register, destination register, is used as an operand is verified, and the instructions which are dependent and which are independent are analyzed. And apart from this, it also analyzes what type of operation. Is it an integer operation or a floating point operation or is a load store? They are done. Once they are done in the hardware, if a particular unit is free, it is scheduled. So instructions are sent to the unit for its operation. Now you have a difficulty. These units are not going to complete the execution at the same time. Integer units will do faster. Floating point units take more time. Load store is in the middle. Depends on cache hit or not. It may take more or less time. So instructions are issued to the units and they all run in parallel and they take different amount of time to complete the execution. Once the values are computed, either addition or subtraction, whether integer or floating point, doesn't matter, some operations are completed, they need to be written back. That write back is not done by these units. Write back is not done by these units. They only compute the values and gets the result. It is not stored yet in the final register. Now who does it? It is done by this unit, completion or retire unit. It is completing the final stage of execution. That is writing back the result into the registers, destination registers. Now, if you have a set of instructions, there may be some destination registers to be written into, and there are some operations to be performed before computing the result and storing in the register, destination register. Now, think of this. If I have an add instruction with two operands, if suppose two operands that are needed for add are available now, what I can do, I can start this add operation to be performed. Now, next I am seeing a multiply operation. I see is a floating point multiplication. Then I can start off the floating point multiplication. Now, imagine I have another add coming here. Okay, add. Let me write it. This is add. This is add. Both are integer add. Okay, I integer add. This is floating point multiplication. These input registers are different, and these input registers are different. Operands are different. And this is writing into some output register, which is maybe R1, and this is writing output into R2. And this multiplication is written into F2 or F1. Now, this is multiplication of floating point of numbers. This is integer addition, and this is another integer addition. Now, let me tell you some clocks. This is taking 2 clock cycle. Assume this is also taking 2 clock cycle. I can as well assume 1 clock cycle, but this is taking 10 clock cycle. Now, they can be started off independently because they don't depend on the inputs are available, and they are not waiting for the input to be available from the other instructions. And we have hardware unit. Now, I start off this instruction I add first. Let me call this instruction I add. I start off in this. Now I am getting F mul. It is coming here. This issue unit looks at this. It is a floating point multiplication, and this can be started off. So it is starting off here. This is going to get completed in 2 cycles, whereas this is going to take 10 cycles. Now it comes here. Result is available. I have to write it into R1. Can I do it? Yes. R1 is written into. R1 is here, so it will again access it here somehow. Okay, some means it is not shown here. Retirement unit is completing the final job of execution. That is writing the result into the destination register, or maybe storing the value into memory. It could be anything. So it is doing it. Now, imagine this unit is completed after 2 cycle. This instruction issue is having this next add instruction ready now, available. Then it knows that it has to be done in the integer processing unit, which is free now. Imagine a situation where these operands are not dependent on any of the previous value. It is available, and the unit is also free. Only thing is, fmul is not yet completed. Fmul is not yet completed. It is still going on here inside that unit. Should this issue unit wait for this fmul to be completed or not? It is not required. If it was a VLIW processor, and if these instructions were packed together in a single instruction, then it should have not been even scheduled. You cannot even pack it because they are not, there are not 2 integer unit in the same instruction. You cannot execute. Imagine, let me give an example. Sorry, I am very bad handwriting. I am not able to write it with the mouse, so you bear with me. Suppose a VLIW processor has packed these 2 instructions separately, because it cannot pack more than 1 integer operation and 1 multiplication operation, because these are the units available in the VLIW. Assume for a moment you have these units and it is a VLIW processor. Now 2 instructions are there. It can only pack only 1 integer operation, 1 load store operation, and 1 floating point operation. And assume that I have only, there is no load instruction. So I will pack these 2 and schedule it on this unit. Now I have a next instruction with the I add and store, suppose. In a VLIW processor, you cannot schedule these 2 while this is going on, because fmul is going to take 10 cycles and this is going to take 2 cycles. VLIW will wait for this 10 to be completed before taking the next instruction packet, because it is statically scheduled and the processor cannot do it dynamically. It doesn't have that intelligence built into the hardware. It's not possible. Now we are talking about something better than that. We have removed that static scheduling which was done by the compiler, and we have now taken care of that scheduling of instructions in the hardware. So we are doing it dynamically in the hardware. We have complicated the structure here. Now we have enough capability to identify if the instructions are completed, I don't have to wait for the next one to be over. As long as the dependency is not there, I can continue to feed more instructions to other units. Okay, so that's a major difference. Let me remove all this nonsense and then explain you once as summary. VLIW, once it decides that instructions are packed and it has to be run on the hardware units, then all of them should be completed. Then only the next set of instructions will be taken. It is a statically scheduled instructions. Whereas in superscalar processor, instructions are not packed. They are coming as individual units. Individual instructions. So the scheduling happens inside the hardware, taking one at a time. If I have a unit free, I schedule it. If I have a unit free, I schedule it. Dynamically, I schedule. I do not worry about the order. So let me explain what happens to the correctness of the program. I will explain to you in the next one. Correctness has to be assured. You cannot just say that I have a hardware unit, I will execute the instruction. Right now, it doesn't have a dependency, but when it is writing the result back, there will be a dependent instruction below. I cannot start running that instruction before the previous result is out. So somewhere I have to take care of the correctness of the program based on the sequence of instructions which is generated by the compiler. So who is doing it? This unit which is below, which is retiring unit, is taking care of it. So executions happen, the executions, okay, only not this one. Execution of instructions happen out of order. I don't have to follow the sequence. I told you add was there, on fmul was there, and another I add was there. This I add execution started executing even before fmul was completed. And in fact, this is taking 10 cycle. I may have another I add which I may start executing. That means execution is not done in order. When I say it is not in order means I am not waiting for this execution of this instruction to start or even to complete until this instruction is completed. What I mean by this, I am not waiting for the previous instruction to be completed for this to start. That is called out of order execution. I don't wait for the sequential completion of instruction. So which is in order, what is out of order? Let me explain now. Instructions are coming in sequence. There is no doubt about it. The instruction fetch is happening in the sequence. So this unit up to this instruction issue unit, it is in order. All the execution happening based on how many units I have, I don't care. If it is free, I will give it, provided I have the operands ready. Okay, out of order, out of order, in order, out of order. Okay, out of order. Now, if you are smart enough, you can know whether the completion or retire unit should do it in order or out of order. Think about it. I'm not going to launch a poll. I still worry about the correctness of the program. I don't want to compromise that. Otherwise, there is no use of me writing a program and then making it execute on CPU. You should make sure that the correctness is assured. So somewhere I have to bring the order. I brought in the out of order in the execution level as long as there are no dependency among them and they can run in parallel. But finally, when the results are written into the register file, I need to make sure that they are in order. So this has to be back in order. So it is like this. initially it is in order because the CPU should know in which order the instructions have come into the CPU. Without that, it cannot store it in the order. See, one thing you remember, the CPU is unaware of what is stored in the memory. It doesn't even know what it is doing. It is just getting some sequence of instruction and executing. Whether it is processing an image or whether it is processing a voice or is it sending a video out on the network, CPU does not know. It knows only some instructions. So if it has to make sure that order is maintained, we should first of all give the instructions in order to it. So it is given in order so that it knows the information that these are the instructions which came in, and then it knows the hardware that it has. So it runs them on this hardware, and then once the completion of execution happen, they again take care of putting the results back in the order so that what was intended by the programmer is taken care of at the end of the execution at least. So what do we gain? You may say that, no, if you are waiting for execution, no, here, do we get anything? Actually, I showed you one example where we got some advantage. We started in executing multiple instructions here when it was still doing one instruction. So we had a parallelism there, and so many of our applications, real life applications, actually fall under this kind of a parallelism. It actually helps you enabling or extracting or exploiting this parallelism. So you can actually start executing some instructions out of order and gain some cycles. Okay, so that's the beauty of Superscalar. Okay, I'm going to be now little faster. Integer unit, these are all you know. Instructions are issued in order, and different execution units execute them in out of order sequence, and completion happens in order again. So in order write back is important for the correctness of the program to be preserved. Okay, so this is the beauty of Superscalar, and which is not the case with the VLIW. Okay. Okay, now let me go back. What are the different data dependencies? If the pipeline is like this, there is no dependency between these two instructions, so they run parallelly without any problem. I am showing you a super pipeline here. That means two pipelines are there, different instructions are into the pipeline. Okay, so it's a superscalar. It's not even super pipeline, it's a superscalar. Two sets of pipeline are shown here. So they are running in parallel. I'm just showing I0 and I1, but actually different stages of instructions, different instructions can be there. It's like a single pipeline, similar to a single pipeline processor, but they are duplicate. It's like a twin pipeline. Two set of instructions will be executing parallelly, but you have to take care of dependency among them. Okay, you have to take care, that hardware has to take care. So if there is an instruction which is here I0, which is giving a result for this instruction to execute, then there is a data dependency. Okay, so I'm only showing the execute stage. Here there may be different instructions. Okay, so don't worry about that. If it is a dependency across the pipeline, it will be taken care of. It is not only within the pipeline it is taken care of, it is taking care of dependency in the data across the pipeline on different instructions here and in another pipeline. That dependency between them needs to be taken care of by the hardware. So if suppose there is a procedural dependency, in the sense we are jumping, the program is jumping to another function call. So what happens is it is changing the context. From this context, it is going to some other function call. In that case, you have to fetch new set of instruction. Branch has happened. So the pipeline is, both pipelines are flushed and the new instructions are coming. So that's why you see that the whole thing is after this clock, both pipeline get flushed and then they are loaded with the new values. So it needs some more understanding. Okay, why this is, what is this shown? Let me explain. Two set of instructions, okay, sequence of instructions. imagine sets of lots of instructions are there, and there is a call. Call means a procedure call, which is jumping to some set of instruction. Now, these instructions were scheduled on the pipeline. Okay. And finally, one call instruction was also here. Imagine it was in this pipeline. When it got executed, this pipeline, whatever instructions are there, they are completed. By this time, it is completed. Now, you cannot proceed with these instructions which was fetched in this now, right? During this time, whatever is fetched, you cannot execute them. So it is ignored. These instructions are ignored. And a new set of instruction from this target location is fetched on both the pipeline. Both the pipelines are fed parallelly. Whatever instructions are coming, if there are no dependency, it can be run through, it will be pushed through two pipeline. It is like if you had a two mouth, you can eat with two mouths. We don't have one. We can eat with both. We have two hands. God is not designed our system with a proper pipelining. He has given two hands, but only one mouth. So we cannot eat more. But here the pipeline is capable of taking in instructions parallelly in both. So when the instructions are coming in, they are fed one after the other. Same instruction is not fed in both. Please remember, two different instructions are fed into both the pipeline and they get executed. Okay. It is like having two assembly line. Cars will come out from both. So that is one way of this. And then another one is resource conflict. If there is a same unit is required, it will be this. Okay. Now, where is the time? Lost my time. What guys? One second again.